So let us quickly do one simple revision of the entire econometrics course. I don't think I'll be able to cover everything, but I'll try to cover as much as I can. So, and this is not the complete course video. You will have to see individual videos for it. It is just the revision, right? Touching up all the points just so that you know what to revise. So you have yi equals to beta 1 hat plus beta 2 hat xi plus ui hat. So you have the simple regression model. Beta 1 hat is the intercept parameter, and this beta 2 hat is the slope coefficient. Beta 2 hat, we have already derived this in one of the video. It is summation of small xi small yi upon summation of small xi square. Small xi is wherever you have a lowercase xi, that means capital Xi minus mean of xi. Small yi is capital yi minus mean of y. Beta 1 hat is y bar minus beta 2 hat x bar. So as far as these are concerned, your regression line. So y bar equals to beta 1 hat plus beta 2 hat x bar is the regression line. So it is passing through beta 1 hat and beta 2 hat. Sorry, it is passing through y bar and x bar. So it means that it is passing through the sample mean. Then the mean of the predicted y is equal to the mean of the actual y. That is also one of the property. We have already done a video on this. Then mean of the residuals is equal to 0. This is the sample regression function in the deviation form. Small yi hat is equal to beta 2 hat small xi. Summation of small yi hat ui hat is equal to 0. It means that the correlation between the predicted y and the residuals is 0. Summation of ui hat xi is equal to 0 means the correlation between the residuals and the independent variable is 0. Then few properties of the assumptions. Few assumptions of the classical linear regression model. One of the assumption is that this has to be linear in parameters. So linear in beta 1, beta 2. It can't be beta 1 plus beta and this beta 2 square. It can be y equals to beta 1 plus beta 2 xi square, root of xi, log of xi. All of that is fine. But not beta 1 plus beta 2, but not beta 1 plus beta 2 square xi. That is not allowed. Fixed x values. So you take up a sample and then the x values are fixed. So you remember our example which we took. So we have taken several families with certain incomes. So we have fixed the incomes, and then for those incomes, we have found out what are the consumption expenditures for the different samples. So you fix the x values. E of ui is equal to 0. Mean of the error term is 0. The nature of x variables. Not all x variables can be same. There is a difference between not all x variables can be same and the fixed x values. So x values are fixed, right? But you take up the different independent variable. I mean, within that, all of them cannot be same. So for example, I say your income is dependent upon education. So education you take up, and if you take all individuals having only 17 years or 16 years of education, then what explains the difference in the income, right? So that is what the nature of x variables is, that because in case if that is there, you cannot estimate the slope coefficient. E of ui square is sigma square, homoscedasticity. Covariance of ui uj equals to 0, serial correlation. Number of observations should be more than the number of parameters, right? So if there are k parameters, then n should be greater than k. Let me remind you once again. We are not proving all this, so it is just a revision which is going on. Properties of the estimators. E of beta 2 hat is equal to beta 2, unbiased estimate. So you take up a sample, you run the regression, you get some beta 2 hat. You take up another sample, you again run the regression, you get the another beta 2 hat. And so on. You just keep on doing this. And then you have several values of beta 2 hat. And then you take the average of those values. So we say that average of those values will be in general equal to the true value of the parameter. Variance of beta 2 hat is sigma square upon summation of small xi square. This is the population variance, right? Covariance of beta 1 hat, beta 2 hat is minus x bar sigma square upon summation of xi square. So your sigma square is the population variance. X bar is the mean of the x variable. Beta 2 hat is a consistent estimator of beta 2. So what is the logic behind this? That you take up the regression, you get beta 2 hat. Then you increase the sample size. You again get beta 2 hat. You still increase the sample size. You again get beta 2 hat. And you keep on increasing the sample size till infinity. And then you will get some beta 2 hat. And when the beta 2 hat, which you will be getting when you are going to extend the sample size to infinity, that is what the true value parameter, that is what the consistent estimator is, right? Gauss Markup theorem. So you take up any estimator, beta 2 hat, we say that's an OLS estimator. It is said to be blue. Blue is what? Best linear unbiased estimator of beta 2. If the following is going to hold. One, it should be a linear estimate. Second, it should be unbiased. E of beta 2 hat should be beta 2. And third, it should have a minimum variance. So you take up one OLS estimate and some other linear estimate. Beta 2 star is also another estimate, but it's a linear estimate. It is also unbiased, but the OLS estimators will have a lower variance than any other linear estimate, linear unbiased estimate, right? TSS is total sum of squares, is explained sum of squares plus residual sum of squares. R square, that is coefficient of determination, is ESS upon TSS. This is also one of the formula for R square, which is beta 2 hat squares into sample variance of X upon sample variance of Y. Confidence interval, you pick up the confidence interval. That is, say for example, you want to check at the level of significance of 5%. So this statement does not mean that this particular interval will contain beta 2 with probability 95%. No. Whether this particular interval will contain this beta 2 or not, that probability is either 0 or 1. Right? So, but the main point is that we'll be able to create such intervals in the long run. We will be able to create such intervals in the long run, which will contain the true value of the parameter. That is what the confidence interval is. And then you have this guy. I have given a video on this, so you have to look at this. That is, how do you get, so you convert this for beta 2 hat, for the slope coefficient, you write the confidence interval, right? Using the t distribution. This also we have done, two-tailed t-test. So you say, you hypothesize that, okay, beta is going to be equal to beta naught. And when it is two-tailed, then alternative is that beta is not equal to beta naught. The test statistic is beta hat minus beta naught upon standard error of beta hat. So once you have run the regression, you have got some beta hat. Minus beta naught is what this value is upon standard error of beta naught. Well, standard error of beta hat. This is distributed as t distribution with n-2 degrees of freedom. Why n-2? Because there are two parameters to be estimated. Intercept coefficient and the slope coefficient, right? Then you take up the critical t. So you want to check it at, let's say, a level of significance. And when you want to do a two-tailed test, you will cut the tails, the equal tails equal area from both the tails. So when you want to check for a, let's say you check for a by 2, right? Again, this we have done in the video also. So you reject H naught if modulus of TC is going to be greater than T star. So whether this calculated T, if it lies here or here, you will reject the null. You will reject the null hypothesis of beta equals to beta naught. Then you have different functional forms, right? So log y equals to beta 1 plus beta 2 log x plus u, right? Log y equals to beta 1 plus beta 2 log x plus u. So this is the elasticity form. So when you have log on both the sides, you will interpret it like 1% increase in x will lead to 1%, will lead to beta 2% increase in y. Okay? Just remember this. जिसके साथ with whichever variable, whether dependent or independent, you have the log, then you will write, you will interpret this in the percentage terms. Okay? Now it is log y plus beta 1 plus beta 2 t ut. So it is log ln model. So if this guy is going to increase by 1 unit, t is going to increase by 1 unit, then how do you interpret this? How do you interpret this? Then you will be interpreting that y is going to increase by beta 2 into the percentage terms, into 100%. Beta 2 into 100%. हाँ भाई log y के लिए कर रहे हैं ना, log से related क्या है? Percentage, right? So you will be interpreting the terms related with log in terms of percentages. So when you say if independent variable increases by 1 unit, dependent variable in this particular case will increase by beta 2 into 100%. ऐसी d को देखिए, d के लिए if independent variable increases by 1%, then dependent variable y will increase by beta 2 upon 100%, right? Then you have yt equals to beta 1 plus beta 2 t plus ut. This is just a linear trend model. So it is just telling you that over the time, if independent variable will increase by 1 unit, then dependent variable will increase by beta 2 units. It is just to see what is a trend, whether it is increasing, decreasing. Okay, then you have adjusted R square. This is used in the multiple linear regression model. So it is R bar square is equal to 1 minus R square into n minus 1 upon n minus k. So you have to remember one thing, that you should not be using R square for the multiple linear regression model. Why? Because with R square, the tendency is that you can keep on increasing the number of independent variables. Residual sum of squares is going to fall. And you will feel very good about our residual sum of squares has fallen. But that is not right, right? So you can also include some irrelevant variables which are of no use at all, and your still R square is going to, residual sum of squares is going to fall, so R square is going to increase. This is not what you want. So R bar square will take care of that, right? There are issues involved with this also, but this is just the revision class. Then remember one thing, comparing to R square values, you cannot compare to R square values if the dependent variables are different. Here dependent variable is log, here dependent variable is y. You will have to make the dependent variable same, then only you can compare the R square values. You cannot compare it as it is, right? Keep this thing in mind. Then in multiple linear regression model, you might have the question like, so you have several variables, y equals to beta 1 plus beta 2 x2 plus and so on. And I want to check whether all of these which I have included from xm plus 1 to xk, are they needed or not? So I'll just think in my head that, okay, all of these coefficients, जो भी coefficient xm1, xm2, xk साथ हैं, वो सारे के सारे 0 हैं. तभी तो significance check होगा ना. Then only you will check the significance. So we are thinking in our head that all of them are equal to 0. And then the alternative is that at least one of them is not equal to 0. Right? Because even if one of them is not equal to 0, then you can't say that all in all everything is equal to 0. हम ये क्यों test कर रहे हैं? If the additional coefficients or additional variables which we have included, should we be including them or not? That is the point. So this is the unrestricted model. Restricted model is you do not have these terms, xm plus 1, say xk. You do not have them. So this restricted model has how many lesser parameters? K minus m. K minus m parameters, right? How do you know this? So in the unrestricted model, you have how many parameters? K parameters. In restricted model, you have how many parameters? M parameters. So what is left out? K minus m. You with me? Huh? So K minus m, okay. You are going to check whether these left out variables, are they significantly affecting or not? That is the point. Then this formula you will have to learn. RSSR minus RSSU, residual sum of squares of the restricted minus residual sum of squares of unrestricted, minus degrees of freedom of restricted minus degrees of freedom of unrestricted, upon RSSU divided by DFU. Upon RSSU divided by DFU. Right? So restricted model may how many restricted model? In restricted model, how many degrees of freedom are there? N minus M. In unrestricted model, how many degrees of freedom are there? N minus K. Okay. So DFR minus DFU करोगे तो क्या आएगा? Your N minus M minus N minus K, that is K minus M. So here you say that this guy is your numerator. This is distributed as an F distribution with this is what? This is K minus M. With K minus M degrees of freedom for the numerator and N minus K degrees of freedom for the denominator. Just keep this thing in hand, right? And there are formulas involved. Given the paucity of time, I cannot derive all this, but I'm just revising these concepts. So you can convert this RSS into R square, right? You can convert this RSS into R square. And then you will have like this. You will again get the critical F. Just say you have got your critical T, you can get critical F also. So what is that? You will check the F distribution for A level of significance, for K minus M degrees of freedom for numerator, and N minus K degrees of freedom for the denominator, right? And then you will see, the rejection rule is that if FC is greater than F star, that is a rejection rule. Then what is there is multicollinearity. So multicollinearity is that if there is correlation between the independent variables, and that is problematic. Why? Because you cannot say that the effect of one variable on the independent variable is isolated or not. Because it can be that X3 is affecting X2 and then you are getting the effect of X2 and Y. No, that's not what you want. You want variables to be totally independent of each other. They should be isolated. There should not be any correlation between the independent variables. You want correlation between independent and dependent variables, but you do not want correlation between independent variables, right? So in case if multicollinearity is present, then OLS estimates are still unbiased, they are still consistent, and they are still efficient. Remember this. T distribution is not affected, so your test of hypothesis are valid. And forecasts are unbiased, confidence intervals are valid. Standard errors and T statistics are numerically affected. They are. But the tests based on them, they are still valid. I mean, ये है कि standard errors and T statistics बदल जाएंगे, right? But test based on them will still be valid. If the main thing you have in your head is that, okay, how forecasts are behaving, then multicollinearity is not a problem. Agar if your main objective is just for the forecast, you can actually neglect it. You do not have to worry much about it. Then what is the effect in the standard errors? Estimates are still blue. Standard errors are usually high. If the standard errors are going to be higher, then what is going to happen to the T statistics? They'll be lower. Right? T statistics, you know now, beta hat minus beta upon standard error of beta hat. So if the denominator is going to be more, then T statistics are going to be less. How do you identify multicollinearity? One way to identify multicollinearity is that in the model, R square is high. But so on the whole, the model is explaining very well. But T statistics are very low. So individual significance is not there. High values of correlation coefficient. So pairwise correlation coefficient between X2, X3, X2, X4, X3, X4, that is very high, right? Regression coefficients are sensitive to specification. So just change the specification, make it a log model, make it something else. And the coefficients can change their value a lot, right? So that is also one way. OLS estimates are still biased and consistent even if the error terms are serial correlation. Serial correlation is that there is what do you call correlation between the error terms, right? You remember in one of the assumptions of CLRM, we have said this, that the error terms should be independent. There should not be any correlation between them. But if there is correlation, then we are asking what are the consequences of ignoring serial correlation? They should be unbiased. They're still unbiased, they're still inconsistent. They're still unbiased, they're still consistent. right? Even if the error terms are correlated and even the forecast based on that, right? But the assumption of serial correlation, no serial correlation is required while proving Gauss-Markov theorem. So if the error terms are correlated, then you will not be able to prove blue. So they are not efficient, they are not blue. They are unbiased, they are consistent, but they are not blue, right? Then how do you check for this serial correlation? So we are going to check it for autoregressive one process. I mean, the correlation between is with the last error term. So you say that this UT is following this. This UT is following this row of UT minus 1 plus ET. So there is a UT is dependent upon the last period error term, and this is the white noise term, epsilon T. Epsilon T is following the normal rules. That is, इसमें white noise term में the mean of the white noise term is 0. There is no heteroscedasticity, no serial correlation in the white noise term, not in the error terms of the original model. So what do? You estimate the model, and you get the residuals. तुमने estimate the model का क्या मतलब होता है? Beta 1 hat, beta 2 hat, beta 3 hat, beta k hat, ये सब निकालना. And then you estimate this guy. And then you compute the Durbin-Watson test statistic, right? Which you have to remember. It starts from t equal to 2 to t equals to n. U hat t minus 1 ka square upon summation of u hat t square, t equals to 1 to 2. And this d is going to lie between 0 to 4. For the positive serial correlation, you will be checking. You will say, no. अगर तुम in case if you're going to put rho equals to 0, then UT is just equal to epsilon T. कोई difference ही नहीं है, फिर तो कोई correlation नहीं है. But positive serial correlation is rho greater than 0. Null is rho equals to 0. This is rho greater than 0. You also calculate rho hat, which is this formula which you will have to remember, right? And D is 2, approximately it is equal to 2 into 1 minus rho hat. So here you say, guys, I need to confess this, that while doing the revision, I'm just doing it as quickly as I can. This is just to tell you the main points in the syllabus so that you can revise it properly on your own. But when we will be doing it in the class, we'll be going in detail about each and every point. So I'm just putting across all the important points so that now when you will open your book, you should remember where to give the emphasis on. And by any stretch of imagination, these are not the only important points, but these are the most important points of the course. So you will have to remember these points, and plus, of course, the extra things. So in case if you have D which is lying from 0 to 2, you will check for positive autocorrelation. From 2 to 4, negative autocorrelation, right? If D is DL and DU are the upper limit and the lower limit. So DL is the lower limit, DU is the upper limit. For the negative autocorrelation, you will write 4 minus DL, 4 minus DU. So there is a D table also which is given. Generally, they don't give you D table, but they give you the entire table or the values which are required, right? So you say that in case of the calculated D, it comes between 0 to DL. You reject the null hypothesis of no positive autocorrelation. If it comes between DU and 2, you do not reject the null hypothesis of no positive autocorrelation. If it comes between DL and DU, it is inconclusive, right? If D is going to come between 4 minus DL to 4, you reject the null hypothesis of no negative autocorrelation. If D is going to come between 2 and 4 minus du, you do not reject the null hypothesis of no negative autocorrelation. But if it comes between 4 minus du and 4 minus dl, the test is inconclusive, right? And this inconclusiveness is the main disadvantage. So it can give inconclusive results. That is the main thing, right? If the independent variable also has a lagged dependent variable as one of the independent variables, just say yt minus 1 also becomes one of the independent variable, it is invalid. If it is only applicable for AR1, so if you have AR2, AR3, this test is not applicable. If the number of explanatory variables become very large, then you do not have the bounds for DL and DU. That becomes, so tests become redundant. And then you have heteroscedasticity. So heteroscedasticity, homoscedasticity was what? That variance of UT is sigma square. Heteroscedasticity what? Variance of UT is sigma square T, which is going to be different for all. Say if you think about it, there are low-income households, there are high-income households. Low-income households that do not have much flexibility in spending. Their consumption expenditure is more or less same every month. Whether this low-income household, that low-income household, that low-income household, every month. But for the high-income household, there is a lot of variability in their consumption expenditure. They can spend a lot, they can spend nothing, whatever, right? So high-income households, they have a larger dispersion around mean. So this is not the case of homoscedasticity. This is the case of heteroscedasticity, right? Similar is also one of the examples which I've given for in case the number of years which you passed you doing PhD and the log of salary. I mean, what is your salary? So that is also variable. That is not same. Okay, after every 5 years, there will be an increase of this much only, then after every 60 days. No, it doesn't depend on just that. It depends upon various other things, right? What are the consequences of ignoring heteroscedasticity? So one thing is that the estimates are still unbiased, they're still consistent. Remember this. But they are no longer blue. Why? Because this assumption of homoscedasticity is required to prove blue. So the estimates are inefficient. The forecast based on them will also be inefficient. These points, consequences of ignoring heteroscedasticity, consequences of ignoring multicollinearity, consequences of ignoring serial correlation, this you have to remember. There are different tests of heteroscedasticity. So let's say we have this model, yt equals to beta 1 plus beta 2 years t plus beta 3 years square t, right? Yt is income, let's say. And then you write the auxiliary regression. So you run the regression, this one. You get your residuals, right? You square the residuals and you say that is equal to sigma square t. So now this becomes the dependent variable. And then everything else is same. Years t square. This is Bruish-Pagan. You run the regression, you get u hat t. This you call that as sigma t. This becomes your dependent variable. And then these things remain same. Years t square as your independent variable. This is Gletser test. You run the regression, you get u hat t, you square it, you say it is sigma square, and then you take log of this. So this thing becomes your dependent variable. And then the independent variables, they remain same, right? So that is called Harvey-Godfrey test. Now you tell me one thing. If alpha 2, alpha 3 will be 0, don't you think sigma square t will be equal to alpha 1? What do you mean by sigma square t equals to alpha 1? It means that it is constant. This variance is constant. It means homoscedastic. No? A constant aa gaya na, that means it is constant. So it is homoscedastic. So this is the null of homoscedasticity. alpha 2, alpha 3, 0. And if one of them is not equal to 0, then it is not homoscedastic, because let's say alpha 3 is not 0. Then sigma square t is what? Alpha 1 plus alpha 3 years t. So it is not constant now. So you run the auxiliary regression ABC, and then there is something which is called the LM test statistic, which is NR square, right? N into R square, unadjusted R square. This is distributed as chi-square with rho minus P minus 1 P minus 1 degrees of freedom. N is the number of observations which are used in the auxiliary regression. Let's say Gletzer regression. P is the number of unknown coefficients. Just यहाँ पे how many unknown coefficients are there? Alpha 1, alpha 2, alpha 3. So 3 minus 1, 2. You get the critical chi-square at 1% level of significance, and you reject NR square greater than chi-square rho minus 1 A. In case if the calculated statistics is more than the critical value, you reject the null hypothesis of homoscedasticity, right? There is one more test, which is White's heteroscedasticity test. So you have x2, x3 there. So what do you do? How do you run the regression? Auxiliary regression, you run the regression, you get u hat t, you square them, and you call that as sigma square t. That becomes a dependent variable. And then you write this. Similarly, you just write x2, x3, square of x2, square of x3, and the cross product term, x2, x3, right? You run this regression, that becomes your auxiliary regression, right? That becomes your auxiliary regression. And then you compute the test statistic, which is NR square. And how many, what are the number of unknown coefficients? Alpha 1, alpha 2, alpha 3, alpha 4, alpha 5, alpha 6, 6. So 6 minus 1. So 6 minus 1. So you find out chi-square for 6 minus 1 degrees of freedom at A level of significance, right? And what is your null hypothesis? But if this, and this are 0, then sigma square is just equal to alpha 1, which is a constant. That is what homoscedasticity is. So if NR square is greater than chi-square P minus 1 at A level of significance, you reject the null of homoscedasticity. This was not a complete class. This is just a revision of some very important topics, right? This again is not a complete course revision. There are topics which are behind this also. But given the time frame, we could complete only this much. I hope it was of some use to you. Thank you, Beta.